just basically an overview of what I did with nanoscience after going through the Institute with Krithika and Angela last year, and what I was able to do with the kids. Because in our district, we're kind of in a flux year. We're switching from discipline specific to integrated all of a sudden, and we have no curriculum. I wasn't really able to think through how to take different portions of what the nano topics we studied and how to put them into units, because I had to develop units from scratch, which I know all you guys can relate to. We're like kind of on our own in science. So I made my own standalone unit because I was so excited about this topic. I wanted the kids to be able to experience what we've experienced, and so I was trying to allow them access. And so my PowerPoints have big letters and big pictures, and so you don't have to be super close to the screen, just to give you a heads up. But I'll go ahead and jump in. So nanoscience, a teaching adventure. So as far as conceptual flow, what did my school year look like? Well, I started off with a unit about light waves, so light wave model, looking at electromagnetic spectrum, light interactions, etc. And a second unit about the particle model of matter, where we got into motion and energy at a particulate level, particle stickiness, particle spacing or density. And then I went into that separate nanoscience unit. In that unit, I broke it down into similar topics as Angela, except my order was different. It made more sense to me to switch the order around for my own storyline. So nano size, nanostructure, building nano, and I didn't quite get to seeing nano. And then of course the school shut down, so we didn't get a chance to go to Stanford. And then after I went into atomic theory, electromagnetism, astronomy, and force and motion as an 8th grade integrated crazy world kind of sequence of content. But the idea is developing a conceptual understanding of the nano by observing visible phenomena. And that's the tricky part, because everything about nano is invisible. It's tiny. So taking the activities from this institute and using those activities as a way of getting to the point of explaining nano, and that making that connection is the tricky part for us as the teachers. So my sequence was basically thinking about some stuff is really, really small and size affects properties. And so I started off with the card sort like we did, and then I did some surface area activities with regard to nano properties, and then I went directly into thin films. And I did the nail polish thin films, and then I went into bubbles and magic sand. And some of the activities I'm going to show you, we haven't done this week, but you'll have access to these ideas and these lessons. And from nano size, first talking about, well, what is nano? We're talking about things that are very, very tiny. Okay, let's mess around with things at a very, very tiny level in a way that we can see the effect at a macro scale so that it's actually visible. And then going into nanostructure, having the kids, giving them the opportunity to kind of look at ferrofluids and liquid crystals. And finally, okay, so we know that things are really, really small on the nanoscale. We can see that there are different types of structures at the nanoscale and how that influences the functionality or the behavior of that material. And then, okay, so if we can't see this tiny, tiny stuff, how can we mess around with it? How can we manipulate it or build with it? And that's when I got into self-assembly, photolithography, and the spherification. Okay, so looking into that. Oop. So nano is between the microscopic and the atomic levels in terms of size. Starting with the card sort phenomenon being the nanoscale itself. And talking to the kids about the importance of nanoscience. I had never heard of it before last summer. My kids had never heard of it. So why is it important and why does it matter? And then starting off with this, does size really matter? Does size matter? And I started off with something in the packets that we received last year, different resources we could access, is having the kids test out the difference of having just food-colored water in a regular teacup compared to a dollhouse teacup. And how does size matter in terms of being able to pour out that liquid? Well, water has surface tension, and when we talk about smaller levels, it allows water to form drops, this surface tension. It allows water to form waves. Water drops can adhere or stick, and so that's the particle stickiness to surfaces even though gravity is pulling on them. And these ideas are part of a conceptual model that if we understand these things, we can explain a lot of things about the world. And especially important, this idea of when we get really, really small, gravity no longer dominates. it's surface tension that dominates. And again, that's part of the model idea of building conceptual model understanding. So surface area to ratio, looking at the cups, we also did the Alka-Seltzer for the reactivity. And thinking about connections, the gecko being able to climb a wall, the little water bugs on the surface of a water, or even the classic, how many drops can a coin hold, reactivity, solubility, and even flammability. Why is it that, coffee grounds or flour, that if you blow it in the air can be flammable or actually can explode? Does size really matter? Looking then at not particularly size, but actually thickness, as in thin films. And we started off with the thin films activity that we did, phenomenon, how light interacts. And then we took that into bubbles, because bubbles are also thin films. And so I had the kids make something that's basically just two drinking straws, plastic drinking straws, built into a frame with yarn threaded through them, and using super bubble solution and allowing them to look at the film between that frame and blow bubbles and look at how light interacts with that film. Taking that one step further, we can actually, now that we know about light and how light waves are different nanometers in length, we can look at the reflections on the bubbles or how the light interacts with the surface of the bubble and actually determine the thickness in nanometers based upon the color, that there's a correlation there. And an example of different kind of questions: what colors do you see? What is the most common color? Measuring the diameter of the bubble, you can actually get any kind of measuring stick like a ruler, and if you soak it in the solution, you can stick it through the bubble without bursting the bubble. So looking at the size of the bubble and how thick is each portion of the bubble, again, based upon the light that you see coming off of it, the coloration. And of course, this ties in with nature, thin film optics and structural coloration, which there are lots and lots of examples in nature of how does the structure at a nano level affect the coloration. And I found this really interesting as well. Can nanostructures in fossils tell us the color of dinosaurs, even though dinosaurs are extinct? And I found an example of information about this on TED Ed. How do we know what color dinosaurs were? And it gets into nanostructures. And by looking at the nanostructures in the fossils, they can actually determine the actual color of a particular dinosaur that's extinct. Moving further along, another example of the thin films is on magic sand. Well, magic sand was developed for industrial purposes, but it was too expensive to use for that. And so it basically got tossed off as a toy for kids. Well, it's got a very thin nano layer of silicon on it, which affects its properties. So comparing regular sand with magic sand, regular sand is hydrophilic, magic sand is hydrophobic. And so these are my kids messing around and looking at the differences and being fascinated by that. Hydrophobic versus hydrophilic. And a quick shot of what that looks like. Looking at connections. After doing that activity, we talked about the lotus leaf, which is hydrophobic on its surface based upon its nanostructures, that water actually kind of beads on it and flows off of it, which keeps it clean and other things. And how those ideas in our nano knowledge helped for the development of something called lotus on paint, which basically uses the same principle to keep it clean and from getting dirty, etc. We can connect that with cell membranes or soap, like some of the videos we've looked at so far. Moving from that size into structure, looking specifically at structure. How does nanostructure affect macro function? And so I did a little bit with ferrofluids, and this is something that I researched. And so I had the kids mess around with magnets, how do magnets attract and repel, and then looking at little bits of iron particles, and how they're attracted by a magnet, and then going from that to looking at something called ferrofluids. So here we have the iron, and then using a cow magnet to attract what is basically a liquid magnet. Okay, this is a picture of looking at that. Moving on to nanostructure and looking at liquid crystals, which I basically just bought some liquid crystal sheets that the kids could mess around with. and putting ice cubes on them or putting them over hot beakers of hot water, or breathing on them, putting their hand on them, different things of that nature, to be able to see the change in color patterns or the coloration, which has to do with the liquid crystals not being a solid, not being a liquid, but actually the structure of the liquid crystals themselves changes with temperature. So they either spread out or come closer together, which kind of, it ties in with the bubbles and the nanostructures of the dinosaurs and some of the other things we've done, the thin films with the nail polish, is that when those structures are thinner or closer together or thicker, more spread out, is that it has an effect on which light waves or what color is reflected off of that surface. And liquid crystals don't have to be just with regard to temperature. There are other things that can affect the crystalline structure itself and indicate different kind of things. And then I had the kids do their nano poster, just like we did, with the discussion diamond, which looks a little different online compared to in the classroom, but the kids were super engaged with that, reading the NAN News. Had them do a gallery walk with regard to the posters. And I just wanted to point out, with regard to conceptual models, if you look at the inside cover of every single edition of NAN News, on the bottom of the page, it literally has a conceptual model. All things are made of atoms, the size, shape, and they have unexpected properties at a nanoscale. That is a conceptual model. And even if we can just get the kids to have an understanding of that, that explains a great deal about the world around us. So then getting to building nano. So we know what nano is, and we've had an opportunity to experience some things with regard to the structure of nano. So how do we mess around with particles, or how do we mess around at a molecular level to be able to build or use this understanding or technology? So then I got into the self-assembly, which ties in with ribosomes and making proteins and DNA replication, cellular mitosis, like Angela said, as far as, well, we are a product of a self-assembly. An individual cell can become trillions of cells. Crystals, snowflakes, mineral deposits, ice, the subatomic particles, when the universe was first forming, those subatomic particles coalesced into atoms, which then combined into stars, etc. So it ties in literally with everything around us in the world. So here are my kids doing the floating self-assembly and also looking at Cheerios. So they were fascinated with their cereal for the whole rest of that week. And so we can model the electromagnetic forces between particles at a visible level with their magnets and their magnetic fields. And so literally what we saw in that activity that we did, that's what's happening at a molecular level, which is pretty crazy. But that activity allows us to make it visible for students so they can conceptualize at the invisible level or the nano level. Okay, and then we got into photolithography, just like we did in the Institute. And actually, I just had the kids go outside, and we didn't get super complicated or crazy. I just literally just had them put the transparency on top of the photosensitive sheet. We went outside, they exposed it for 1 to 2 minutes, then we went back in the classroom. And it darkens by the next day, so they just kept it in their folders. And the next day, they had really dark images on there. Then we did spherification. And so these are my kiddos doing spherification. And using that idea of polymer cross-linking. In other words, all of these ways of manipulating at a nano level, it actually involves chemistry. But, you know, in the 7th grade, 8th grade level, we're not getting really deep into chemistry like you would in high school or college, but just this ability to see something happening. And if we know that this is how it happens, manipulating materials in this way, that we can apply that. And we can apply that, for example, in the nanomedicine or other things that we can connect it to. So in terms of what I was trying to do with the kids, I was trying to get from a place of experience using these activities to a place of understanding something that's extremely abstract, which is the nanoscience and the nanotechnology itself. And so what I ended up using was a sequence in each one of my lessons throughout this particular unit of starting first with observation of phenomenon, with each of these different concrete activities. So it's big enough for us to see, we can manipulate it, we can experience it. It's using our senses and our hands-on approach, and then recording those observations. In each one of my lessons, I had some way of the kids drawing or labeling what they're observing. So taking that from a three-dimensional experience to a two-dimensional representation of what they're observing, and then discussing it. So processing what they've seen and experienced, what does it mean? What's happening? What do you notice? And asking them questions to help them get to a place of making sense of that experience. And then, as Angela has done with us in the Institute, is once we have experienced it and we have some ideas, but we don't know where else to go with it. Like when Angela's asking us, well, why does that happen? I don't know. I'm not an expert in nano. I don't know. Well, that's where you give the kids resources and allow them to watch a video clip. And then once they watch that video clip, they can tie that to what they've experienced and discuss further and provide scientific articles. And that gives them the opportunity to boost vocabulary, have different ways of explaining or expressing what they've observed and building on that to finally get to the point of the abstract understanding that they can write, because language is an abstraction, to be able to write about the explanation of why that happened. And then it also allows them access to these scientific articles that if we had just given them an article out of Scientific American, they would have just tuned out because there's too many big words and it doesn't make sense and I've never seen it, I don't understand it. But by the time you get to the end of that sequence, they can read the article and they can engage with it and understand the concepts. Okay, and then getting back to what we talked about, I think yesterday with the next gen science. So starting with the driving question of what is nanoscience, what is nanotechnology, and taking the students down this road, which is paved with a sequence of activities. And that sequence of activities is our storyline. How does the story make sense to us as individual teachers? Because we are the storyteller, or we're the ones leading the kids through this story. And then as the guardrails on that road to keep the kids on the road to a full understanding as we connect these different ideas, using essential questions along the way and little questions within and during the activities. When the kids ask, why did that happen? Posing questions back to them that are kind of like breadcrumbs that lead them to smaller understandings that over time build into a conceptual idea. Oh, I get it. Oh, is that why geckos? Oh, is that why? Oh, okay, the butterflies and the bubbles and all these things connect. And then finally we arrive at a set of ideas, which is our conceptual understanding. And that's what we call the model. Is in model-based reasoning, that's what we're going for, is that conceptual model. And if I have a good conceptual model, I should be able to look at a different phenomenon that we haven't specifically discussed and be able to take that information, that understanding, and apply it to something new and explain that and go, oh, it's like the so-and-so activity, or it's like what we explained when we were talking about. Okay, and so this is a conceptual model. What Angela presented to us in the very, very beginning, what's so special about nano? That if we can figure this out and help the kids have an understanding of some of these ideas, and then pair that with examples in the natural world around us, and then with the nanotechnology of how it's being used right now because of our research and understanding of these concepts, that opens up a whole new world to our kids. That there are careers in nanotech, that there are all these new research advancements that are being made. I read an article recently that upwards of 80% of the latest innovations are coming out of the field of nanotech, nanoscience, nanotechnology, which is pretty cool. And that's it for that.
Thank you, Jenny. That was awesome. Okay, Justin has a question. Was nano planned to be a theme during your entire year?
It wasn't until I went to the Summer Institute, because before I did the Institute with Angela last year, I never even heard of it. I had no clue what it was. I was just super excited to go hang out with people at Stanford and like learn something. And when I got there, I felt like a dum-dum because I'm like, I don't even know what these people are talking about. And it's okay to feel that way. I never heard of it, didn't know anything about it. And half the time I'm like, I don't understand what the explanation was. I still don't get it. So I went back and I did a lot of research, like what you guys are going through right now. Don't feel like you're dum-dums. You're not. I literally didn't know anything. I know, okay, there's atoms and molecules in the universe, but I had no clue what does this have to do with this whole new word nanotech? But what you've experienced so far, as far as watching a video, and then you're like, oh, okay, I'm starting to connect that to the activity. That's exactly the process the kids go through, which is pretty amazing because by the end of it, they knew so much stuff, they like went past me.
Yanette also has a question. Did you have to purchase any of these materials?
Well, yeah, in my district, they give us this much money for science, literally. So I did, and so that whole teacher way of surviving and figuring out where can I find cheap materials, and how can I improvise. And so if you have questions specific to any of the activities, I can give you suggestions or talk to you about how I made it work. You know,
Mhm.
being a teacher and poor and having nothing to work with.
Yeah. June had a question. Was this an entire year of content, or how long? What did this take to teach?
I think I spent about a month on it. But like I said, I was building on already having done a particle model of matter unit and a light unit. So it was actually taking the kids to like high school and college level thinking on those same topics. And then when we got into astronomy, the kids were on point. When we were talking about electromagnetism and astronomy, they were bringing things up that I'm like, oh, how do they know that? And I'm like, oh yeah, we studied nanoscience. So there were some really awesome connections that, like I say, the cool thing is nanoscience underlines literally all the content, everything we teach, literally. It's just a matter of figuring out what are the examples and how is it being used in technology. Because you could name any possible topic in science, nano is connected. And I didn't know that when I first went in. I'm like, what is this? It's probably irrelevant.
Mhm. Are there any other questions from anybody? I know that was a lot to process. Jenny went through a really deep dive of stuff, and yeah, it was very. I was really blown away by what she did. So yeah, that's why part of the reason why I invited her and Krithika, because they just did such great job. So I thought they could sort of help you and sort of be the bridge between the nanoscience stuff, but also the teaching stuff, and provide a good
Sorry,
perspective.
sorry for going so fast. Angela had me on a
I can't. Yeah,
and
I
I
did.
did it in 20 minutes. See, are you proud of me?
Yeah.
And the other thing too is that like for a couple of there's 3 activities that I mentioned that are not what you guys did, but I actually provided my actual lesson with the article, with the teacher, or the student handout, and the whole 9 for the magic sands, which
Mhm,
is not super expensive. I bought like 7 bags of magic sand and only used 2. If
mhm.
you're conservative and you reuse from the last class, don't let the kids mess it up, and then reuse it. So super super cheap, the magic sand, and then the liquid crystals. And
Yeah.
same, I didn't buy tons of sheets because it costs money. So, but I let them share in their groups. So,
Yeah, and that one, I will talk about them a little more, or actually, it might be better. We might be better suited to talk about that now. Actually, I don't know. Do you guys? So the plan for the afternoon tentatively was to sort of do more time to either do breakout sessions or open discussions on the lesson for lesson planning, obviously. But I can also do a quick overview of what we plan on doing, or what additional sort of hooks or activities would be useful for you. Yeah, Leo has a good point of creating stations will help reduce costs with sets of things, as well as sharing materials. So yeah, anybody voting for additional experiments and or activities? All right, we're a little bit across the board. Why don't I try to spend as little time as possible on the activities, so then the rest of the time you can spend on the the and then which is also nice, because then tomorrow morning that we will be able to have some work time in the morning as well, so we can start off with some morning work time as well. Does that sound okay? Because this is actually stuff that I was going to talk about tomorrow. So we're kind of a good mix. All right, perfect. So a couple things that I wanted to do was talk about um, some hooks, and I think TV is an excellent way to do that, or movies. So I don't know. There's this Ant-Man scene. I think I'm gonna skip. I need to skip through some of it. Oh no, there's a video. Or I mean, what is it called? Advertisement. Um, well, ignoring the advertisement, but this is a nice example from Ant-Man. on how things can sort of shrink down. He talks about, he was like, I think during he's like he makes himself like now. All right, well, we're gonna skip this one. But this whole clip, which is also loading a little poorly, is just to show, all the different sizes and shapes, and how small someone can get. And I think later, so yeah, he becomes like nanoscale.
All constants.
All right, I won't go into too much detail, but you kind of get the picture, right? You can ask the kids, oh, what would it be like to be that small? Or, how do we think about, being so small, you're the size of molecules. So I think it's a really nice hook to sort of engage your students and then start that conversation. It's kind of the thing that Jenny was talking about with the phenomenon, like hook them that way. Another way is also through a superhero. Oh no, this video doesn't work. All right, I will update it. But anyway, the video is basically where Iron Man, he has like a new suit every movie, right? And the last one I think is where he has these nano robots that sort of self-assemble into his protective wear. So that's another thing. So one activity actually that is sort of drawing from after doing a nanoscience unit or talking about the nanoscale properties is to really focus on like a nano superhero, right? So leveraging some of these properties to say, okay, well, if you wanted to design a nano super suit, what would your properties be? So that could be also a fun and more like imaginative way to think about science as well. Okay, so another couple of bonus activities is the super hydrophobic surfaces. It's again something that's biomimicry. It's very similar to what Jenny talked about with the magic sand, but you can buy this spray. It's called Never Wet, and you can spray it on material. Usually it's like for cloth, to protect your shoes or protect your pants. But it's actually nanoscale material, and it's also focused on the biomimicry of a lotus leaf, as well as some other plants that are super hydrophobic. They are obviously hydrophobic, but then they have this nanoscale structure that you can zoom into, like over here, where they makes it even more hydrophobic because there's so much surface area. So that one is really interesting, and I have linked it below. Another thing that I really love is this edible wafer. This one is like very sugar intense too, obviously, but you kind of learn how the engineers inside the clean room can make wafers out of your own cookie. So it's really thinking about the process of patterning something patterning something really precisely, which is what we kind of did with the sunprint lithography, photolithography one, and then here. So this particular student actually carved into the cookie, which thought was really cool, and then put frosting in. Some people, they use two different types of frosting, but you actually have to think about when you put down your mask, to put your pattern down, what size. So, there's multiple sizes of sprinkles that you can play around with and directly deposit, or use different types of frosting to deposit. Like this one, you can tell somebody just spread it with the pink frosting, but then they used a tip to then deposit the other types of frosting. And to be honest, that's actually very similar to the way you deposit certain materials down, right? You can deposit materials in one thin film, or you can deposit them down, atom by atom, or in a specific pattern. So I think that's a really cool example, and obviously very delicious. Another one is invisible sunblock, and these are all linked to in the resource page, but they're under day 4 that says additional activities. Invisible sunblock, way in the beginning, I was talking about, why is sunscreen really easily can be easily rubbed in or pretty clear these days. And a big reason why is because of the particle size in the sunscreen is much smaller. So you can take different types of sunscreen and then wipe it on a piece of paper, and you can ask the kids, which one do you think is the nano one? Which one do you think is the non-nano one? And have a discussion. And there's a whole explanation and lesson that's attached to this. So I won't go into more detail. Okay. And then a couple other things. So again, the resource page. So let's talk about that. It's already up on the homework, so you can directly access it. But I wanted to point out a few of them I think that are particularly helpful, which is the NISENet. The NISENet one, June, I actually posted one that's specifically for water purification. And Dustin, the one with the mittens that I was talking about, is also posted on the NISENet. Nano.gov, it's an actual government initiative. So to really focus on nanoscience, nanotechnology in obviously research settings, but also in educational settings. So this is a really nice place to get really nicely vetted pieces of information that you can use. Also, they have a little newsletter and even a podcast interviewing different types of scientists on nanotechnology and nanoscience. And then third, this is actually the network that I'm part of. We have a whole source of additional resources that you can use. So I am not the limit. So if you want to do something outside of it, may better fit you, please go for it. Please do the research. Like Jenny, I did not tell her about liquid crystals and she went after it like nobody's business. So which is great, which I really applaud. I don't want to dictate, whatever is going on in your classroom. So if you, still want to do nanoscience, but want to do something else, please feel free to do that. And I'm here if you want to ever ask me any questions or clarify anything. So I think that should do most of it for the activity. So that gives us 15 minutes. We can do a little bit more discussing. If you guys want to do a breakout room, I'm happy to do that. If anyone wants to, I know Fiaz and Samantha were discussing earlier, so I can put you back in there, or anyone else, has a particular person they want to work with, I'm happy to do that. So yeah. And then while you guys are deciding that, or maybe deciding on teams, I wanted to just go over again tomorrow. So, okay, breakout room for Samantha and Fiaz. I'll do that. So again, for classroom, the Google Classroom for tomorrow, you don't really have any materials besides your lesson plan. So your lesson plan, it's really up to you what you want to do. You can do a full presentation like PowerPoint, or you can present that lesson template that was uploaded, or your own lesson template. It's really free form, but please expect to present for about 5 minutes and then like a minute or two for sort of feedback, okay? And if it's a teaching team, that's totally fine. But yeah, we'll try to be a little bit flexible on that. Does that make sense to everybody? And again, it's gonna be a safe space. Like Jenny said, this is all new information. So we are, there's a lot of grace here where, we're learning remotely, we're learning new content and trying to teach new content at the same time. So if there are mistakes, we'll provide feedback, but provide feedback in a nice way. So, all right, does that sound good? Okay, so please, I see some breakout rooms, so I will start making them. If anyone else wants to make any breakout rooms, I will do that. Oh, and then Dustin has a question for Jenny. Feel free to ask. Okay, Amrit and Vicky.
Yeah, I didn't want to interrupt your
No worries.
Okay. Yeah, so because thinking about how to add nanotechnology to curriculum, was for a 7th grade class, or was 8th grade, right, Jenny?
It was an 8th grade class, and it was my first year teaching 8th grade in like 10 years. So I hadn't taught 8th grade yet for the NGSS. And then plus the district last second switched from discipline specific to integrated. So it's a crazy mess. The topics I have looks like a crazy mess.
Yeah.
It all relates. I mean, I did the life sciences stuff for 10 years. So it makes sense to me. Like we're going to have to do DNA also. Yep. And that's totally awesome for the self-assembly and the information. And I mean, it's just.
That's really cool.
Yeah, thank you.
Yeah, because I struggled to have my kids really connect with a lot of the smaller things that were happening. Like we did physical and chemical changes, but trying to talk about what's happening on the molecular level, they just had no connection to it. So I was thinking about like an intro unit
Right.
where students like start with you just had your meter stick sitting on the table and the cards, but really got them thinking about the smaller scales and working down and maybe trying to combine it with some pictures of things and
Mhm.
starting with just what you can observe with your eyes and then taking the microscope out looking at that but have the units there as well so that the practicing measurements and then working down to like, all right, what are the limits of the microscope? Why doesn't light work there? And then look at these uh, pictures from the other viewing technology that we have. Um, but I thought it was really interesting the way that you set that foundation. The students were able to connect to so many other things. That was really cool.
Right, and that's where the conceptual models come in, is that if a conceptual model or model in the NGS sense is a set of ideas, then once they have that set of ideas, they become more powerful because they can
Okay.
look at all kinds of things and go, oh, I know how to explain that, even though we didn't talk about it in class. They
Mm,
start making their own connections and explaining things. But
yeah.
you're right, as teachers, the hardest thing is to figure out how can we help them understand something that we can't see.
Yeah.
And so what Angela presented, all this amazing content, that's where we pick up the ball and we go, okay, so we have this cool activity about something we can't see and we don't understand.
Yeah.
How do we let the kids mess with this and then have an idea in their brain to explain something invisible?
Yeah.
That's where the teaching part comes in, where we have to say, okay, what can they see in this? What is this representing? What is this um, modeling, but not in the sense of conceptual model? What is this, like, the little foam floaty things? Well, each one of those is a molecule, right? And they attract each other. Well, at a molecular level, they attract each other. And so you're thinking about, what can I let them see and mess around with? And then what does that allow them to know? And
Yeah.
then as teachers, we have to provide things. Like, one of the things in NGSS is getting away from teacher talk, like where we tell them
Yeah.
all the answers. I don't
Yeah.
tell my kids any answers. I say, oh, you're curious about that? Here's an article. Let's watch
Yeah.
this video. Here's another activity, or I ask them another question that's going to help them get to that point.
Yeah.
And so that's where, as the teacher, we're figuring out what is that sequence of questions that helps get them there. And if they're stuck, and that's what the guardrails are for in that
Yeah.
analogy, is, okay, they're stuck right here and their car's facing the wrong way. What can I let them see? What question can I ask? Or what resource can I provide? And then allow them to talk to each other or think it through, and then kind of help them, and their little car gets turned around and they start going the right way. Oh, and then that's when you have those aha moments where they connect.
Hmm. Yeah, it's really neat. Yeah, there are definitely scenarios where I was so tempted to just, stand there for like 20 minutes and just tell them everything. And they would have probably been at the point where about half of them would have understood the language and been
Mhm.
engaged to understand it. But yeah, definitely letting them play with it. And I think that the small stuff and a lot of activities that you showed really got me excited for things that I could do. Right now I'm teaching seventh grade. Um, and there's that was my first year teaching, so there's so much improvement that's gonna happen. And I think a lot of the stuff that you've come up with is really inspiring for that. So
Well, on a side note, if there's anything you'd like on certain topics that I can provide to you outside of the institute, I'm welcome to be a
awesome.
resource. And Krithika too, I'm sure. I mean, I'm volunteering, or I'm like, hey, Krithika down there.
Yeah, and now of course I have great coworkers that are also always looking for great activities and sharing stuff. So
Awesome.
yeah.
All right. Any other questions, concerns? I'm gonna stay on for a little longer. I know, but you don't. If you're gonna work by yourself, feel free to leave if you want. Otherwise, I'll stay on for a little longer to keep the breakout rooms open and stuff.